today. Now we finally sort of get into the actual, maybe, details of certain approaches to sampling these sorts of configurations of SU3 matrices that it turns out describe physics for one reason or another under actions that look maybe something like this. So this being then the potential function that gets exponentiated to determine the probability measure. And the question is, how now should we sample these many degrees of freedom on what could be up to very large lattices efficiently? So let's first answer the question maybe of how we can sample at all, and then we can talk a little bit about efficiency towards the end. So let's talk about Markov chain Monte Carlo for these sorts of models. So I imagine I don't need to say too much about the details of Markov chain Monte Carlo to this audience. I'm assuming it's fairly familiar to most of you. But let me, just for the sake of writing the notation, kind of sketch on the board what notationally I would think about as the components of a Markov chain Monte Carlo process for a lattice field theory. So generally speaking, of course, the idea is that you'll start with some maybe initial sample, and then through a series of stochastic transformations, produce a chain of configurations. And these stochastic transformations are designed such that the equilibrium distribution for a large number of steps is the distribution of interest. And now there are many ways, of course, that one can design these transition functions. But a sufficient condition is to satisfy detailed balance. And so the meaning of this, in the language of our gauge field configurations, our gluon field configurations, and our action is simply that the probability density associated with some original configuration U times the transition probability from U to U prime should be equal to the kind of converse of this, where T is the process that maps from one configuration to the next. So this is a sufficient but overly stringent condition that ensures, well, if we deal with questions of ergodicity, ensures that the Markov chain should converge ultimately to some kind of distribution with density given by our normalized weights. And so, okay, we can work with fairly simple approaches to sampling already and make some progress on this lattice field theory problem. So we can do something fairly akin to these kind of single site flips that worked in the Ising model. And we can ask, well, maybe there's some local process that we can do on single gluons, so on single gluon variables on a given link of the lattice. So let me call this something like single link updates. And of course, the idea is that if you design such a transformation that works and satisfies the appropriate criteria for one link, you can then sweep over the whole lattice and do iterative sweeps to update stochastically your configurations. Yeah.
So to go through the whole lattice, then you're better off to just compute the integral analytically, or?
No, what I mean is, so let me look at just one link of the lattice at a time. And so this is one 3x3 matrix inside the whole configuration, and just update that component of my configuration. Yeah. Okay, so the idea is, yeah, just to give that some notation, we want some kind of local transformation that takes this variable or this part of my configuration u mu x and update it to some u prime that of course somehow depend on the context. And because our action is structured in this way, what that context really amounts to is, well, what is the value of the links on all of these neighboring squares? Okay, I've not given myself some room. Hopefully you can imagine what that looks like. And I'm not going to draw the other two dimensions because this diagram gets very chaotic. But in 4D, you have 8 neighboring plaquettes, or 1 by 1 squares, that determine what the weight should be, or what the probability should be of this given link conditioned on its neighbors. Now, a fairly straightforward approach to this is to apply some kind of symmetric, let's say, proposal. So a proposal for an update to a new link, and then accept or reject that update using Metropolis Hastings accept reject step. So let me be concrete about what I mean by that. So a symmetric proposal should, of course, respect this fact that my variables are SU3 matrices. And that makes this a little bit trickier. But one can still construct a useful symmetric proposal by asking or sampling some sort of 3 by 3 matrix A that can be exponentiated and multiply my link variable from the left, my gluon from the left. So just to be clear, this is really some kind of 3 by 3 matrix here. And this is our original 3 by 3 matrix. And so the proposal is to multiply this randomly generated matrix from the left onto our link. Now, to make sure that everything remains appropriately in this SU3 matrix group, we need this A mu to satisfy a few criteria. Happens to be the case that this needs to be a Hermitian matrix, so it equals its own conjugate transpose, and it should be traceless. And if these two properties are true, then the product of this exponentiated thing with U gives you something that remains in this SU3 group. So somehow, if you like, the trace being 0 maps onto the fact that the determinant remains 1 after exponentiation, and this hermiticity maps onto the fact that the matrix remains unitary after multiplication. OK, so now to actually draw these, you can imagine I draw this from some sort of normal distribution or whatever you like, as long as the probability of this proposal from U to U prime should be equal to the probability of proposing from U prime U. And that is the case as long as we have something that's symmetric under A, this matrix A goes to minus A. So all the entries get negated. Because if I, of course, stick a minus sign in front, then after exponentiation, this is the inverse matrix. And so it'll map, if I multiplied that onto the right side, it would be the opposite direction of this transformation. So that's a fairly easy distribution to concoct. For example, I could sample all of the entries of A from some normal distribution, which is symmetric about 0. And then I can just project it onto being Hermitian and traceless. And that is just some distribution for a proposal that we can work with. So then, of course, we must deal with the fact that that by itself doesn't satisfy this detailed balance condition. So we should apply some kind of acceptance probability. And the appropriate probability for such a symmetric proposal is simply then given by the ratio of the probability of the new variable divided by the probability of the original variable. So this ratio of the two weights. Notice that, by the way, this potentially unknown normalizing constant cancels out. So this can be performed even if we haven't gotten an estimate of that normalizing constant, which is convenient since it's often difficult to do so. And let me just make clear, this is the probability then to transfer or transition from this value U on this one link to the value U prime on the same link. So this is a one link update. And this can then be swept over the entire lattice, or so over all the link variables to define some kind of composite Markov chain update to the entire lattice. So ultimately, of course, the efficiency of this is somehow going to depend on how quickly you can mix up and decorrelate the configuration on your lattice, which depends on how large or how wide the distribution over these variables are, determining how far the link variables each move along in each step. But also that has to be traded off against the fact that if you take a very big step, the ratio of these two weights might be small, and so you might very frequently reject the proposed update. So there's some kind of trade-off here between the acceptance rate and the step size. It's fairly easy to tune this, and so you can just come up with some reasonable-looking proposal that accepts, of order 50 to 70% of the time, and life should be good. Except that's not the only source of correlations in such a Markov chain update, and the other source is coming from the fact that you're just doing these local updates. So now we can think back to what Michael presented about the Ising model. If you're ever in a situation where there's really these kind of long-range correlations where all the field variables somehow in some patch very strongly want to remain aligned, maybe that's a result of tuning the coupling constants, these prefactors in your action in such a way that, for example, the lattice spacing is effectively very small. That is, in fact, exactly the limit we would like to go to. Then it's very difficult to update each link very far without breaking this kind of correlation. So you'd have to take very small steps, and the probability to collectively update large patches of correlated variables is very low. And so in general, one expects this to have fairly bad or fairly severe autocorrelations, meaning that you need to take many steps of updating before you have an essentially decorrelated sample from your Markov chain. So thus, especially as we go towards this continuum limit, which is somehow similar to the very cold temperature limit of statistical models, although really physically is not in any way related to cold temperature, but has this similar structure, then we suffer from this difficulty if we take a naive approach like just taking single link updates. But there are more complicated approaches that do a bit better. So I'll leave this action up here because I think it's useful to refer back to, but then we can continue below it. So instead of using these kind of single link proposals for a new value and then an acceptance or rejection based on a Metropolis-Hastings criteria, instead one can perform what is known as heat bath or Gibbs sampling. And I hope this is the same usage as what is meant by Gibbs sampling in your context. I'm never sure in terms of terminology, but at least in my language, I would say this is Gibbs sampling. And so what I mean by that is that rather than propose symmetrically some kind of update to my link, instead I just look at the conditional distribution of this link given all the neighbors. And this is something that you can straightforwardly compute from such an action, because this can only at most depend with such an action on these directions of links in these neighboring squares. So there's some finite number. It's a finite dimensional distribution. In principle, this is something you can write down and treat. And then by some tricks, you might be able to sample, just directly resample the value of this field variable given the neighbors. So this is perhaps slightly more in terms of the autocorrelation time. However, it is more expensive because you're doing the construction of this complicated distribution and some kind of direct sampling from that distribution. And in fact, I think the most efficient formulations of this usually involve some kind of hybrid where you say, I'm going to propose not a symmetric proposal, but I'm going to propose a rotation. So, well, rather a left matrix multiplication by some variable in a restricted space. So, for example, I might restrict to just a 2x2 submatrix, and then using the known conditional distribution over that matrix, I'll sample this 2x2 block. And so your proposal then is not a symmetric one, but rather is one that's tuned to automatically prefer the distribution according to the action. So this sort of proposal does not require an acceptance or rejection step. and can therefore, in principle, mix much faster if your major obstacle is the local updates per links, and is not, as I was talking about previously, the large-scale correlated updates that need to happen as you go towards the continuum limit. So this can be effective, but there is this important limit in which neither of these fundamentally address the sampling problem. However, I should note that because of the efficiency of something like this, combined with some other practical improvements, if we forget about the quarks and we just talk about this action and we say, all I want to do is simulate the theory of gluons alone, which can be described by just this action and just the fields U, then something like this heat bath plus some tricks can work fairly efficiently, since the alternatives are maybe improve the autocorrelation in terms of your Markov chain time, but correspondingly increase the cost per step so much that it's not worthwhile. So this is, in fact, if we just simulate gluon dynamics, often used. So I'll just make note of that. However, the more complicated problem when we add in that extra weight that comes from the quarks is certainly not going to be easily treated by this method or this method, because there's actually a nice computational simplification that happens when your action is local like this that doesn't apply when, I should also jot this down, when we have something from the quarks that introduces this determinant. And what I mean by that is in this sort of a local updating and then acceptance or rejection step, while in principle we're computing the action over the entire field configuration and then taking the ratio of the new configuration by the old configuration, since this action is the sum over many terms, many of which don't talk to that link at all, we can just drop them from this calculation. So this is really some kind of local calculation that only has to do with the change in action of any terms that touch the link that was modified. And so this can be quite an efficient calculation, even if you have a very large lattice. And likewise, for this heat bath or Gibbs sampling, these neighbors which go into determining the distribution are localized near the link. And so you don't have to do something that talks to the entire maybe 256 to the fourth lattice each time you update one single link. However, if I have, something like a determinant of some matrix as part of my weight, this, in principle, makes every link interact with every other link, however weakly. So you have not an ultra-local action, as I would call this, but you have some kind of localized but falling off action at large distances. And so if you want to treat that exactly, you still need to deal with all of the possible pairs of links in even these local methods of calculating updates for one link at a time. So you expect it to decay exponentially. So there is some kind of localization scale, but still non-zero interactions even at arbitrary distance. Yeah.
I guess that's possible to do with the fact that it's infill rather than outfill, because somehow you're imagining in the continuum while you have the correlations. So maybe your approximate discretization would go away somehow.
So this one's a little bit funny because actually the exponential localization is something that's somehow proportional to the lattice spacing, meaning actually that changes as you change your discretization and goes towards a local interaction. However, still, because you have these tails which are non-zero, which you don't really know where you can safely truncate, you have to, in principle, deal with arbitrarily many terms, arbitrarily your entire lattice, I guess, for such updates.
Do you get problems with going to like if you have to sum through the copies of the lattice as well?
You mean the copies in this imaginary time direction that we were talking about?
No, like so you've got periodic lattice. So if you take an arbitrary number of loops through the lattice, do you still have to look for those combinations?
So, I mean, fundamentally, the most complex thing that could appear here somehow is just some weight that's a function over all the lattices on your fundamental zone or fundamental cell exactly of your lattice. Because everything else being a periodic copy, you can already compute the effects of that exactly. So there's computational tricks is what I'm trying to say. That means you don't have to worry about any sort of infinite repetition like that. Yeah. OK, so to summarize, we have these nice local updating schemes. They work well when we focus just on the gluons. But because of this somewhat non-locality of the effective distribution introduced by the quarks after integrating them out, we really can't efficiently apply them in those cases. And so something more needs to be done. And what is really the kind of workhorse of modern day calculations is what's known as hybrid Monte Carlo. So this is an approach based on some kind of continuous updating, if you like, of the fields according to some fictitious dynamics in a way that lets you coherently update your whole field at once, and does so in a way that really fairly efficiently decorrelates your field configurations. So I'll just note, I mean, this hybrid Monte Carlo, I imagine some of you are already familiar. This is used in also, I believe, in some Bayesian statistics contexts and many physics contexts, not just quantum field theory. But as far as I'm aware, this was introduced first in a paper in Lattice QCD in particular. So the driver of generating this, this method was Lattice QCD in some sense, because of simply the challenge required to treat especially determinants of this form, which introduce this somewhat non-locality in the weight function. OK, so how exactly does this work? Well, it's still a Markov chain Monte Carlo approach, but we introduce fictitious momenta. So this has nothing to do with physical momentum in any sense in the physical theory. It's just a variable, which I'll denote with pi sub mu x, that goes with every link u. And the idea is that we can define an energy or a Hamiltonian, if you like, in terms of not only our original variables, the u, but also these momenta that are conjugate to the u, and perform some kind of molecular dynamics or Hamiltonian evolution on these pair of fields. And the idea of this is, if I have some kind of momenta, the momentum will be imparted in some sense onto my field. It'll follow the momentum. But also, if there's a potential which will be written in terms of the action that's acting on those fields, there will be some kind of exchange of information between the momenta and the fields themselves. And this provides a nice way to somehow stochastically update the fields as a whole in a way that fairly effectively decorrelates them. So I'd better say what this Hamiltonian or energy function actually looks like in terms of the u and the pi. So first of all, you have a fictitious kinetic energy term, which I'll introduce yet another inner product sign to denote. So this is something like just the momentum squared summed over all of the lengths of the lattice. And then you have some kind of potential energy term, which is simply our action, whatever we happen to be choosing or simulating at the moment. So x is still the sites on our lattice. So mu x rather, I mean, together you can think of mu, subscript mu and x as denoting that it's associated with this link of the lattice in the mu direction. But now, rather than just having this SU3 variable u mu x, now I've also associated an extra variable pi mu x. It's also, if you like, it can be represented also as a 3×3 matrix. And the point is that whatever we happen to have for pi, as we go forward in this fictitious time, it'll update u, and then the function of u, based on the potential, will update the momenta. So I should note that we're talking about momentum in some kind of group space. So not to go into too much technical detail, but the upshot of this is that much like what we did for the single link updates, if I want to somehow define movement in a direction within this SU3 group, so okay, maybe I should say what I'm trying to discuss here is the details of the SU3 group structure. So if I'm trying to define a movement or momentum in some direction, I need these variables to be elements of the Lie algebra of SU3. Okay, so that's fancy words, but what that actually means is exactly the same thing as the A mu that we saw before. So the idea is that for some small step of time, a fictitious time, having nothing to do with space-time, by the way, dt, I can update each link by multiplying by the exponentiation of this thing. And so if we impose on this pi the same constraints that the trace is 0 and that it is Hermitian, then the output variable will remain an element of this matrix group. And in fact, what I've written here is exactly the statement that it's in this algebra. I just wanted to gloss over that before, but now in case you're curious to dig into the technical details, that's why. So this same condition applies to our momenta. And in that sense, the momenta can describe the direction within this group space, which otherwise, I mean, I haven't talked at all about what SU3 actually looks like, but it's really some kind of maybe non-trivial, possibly curved geometry in a higher dimensional space. And so otherwise describing momentum in this space would be a fairly tricky thing to do. So it's convenient that we have this language. And now what I should be careful about is, well, what does this kinetic energy term actually mean? And then how do I update the momentum given the field? So I've talked about how the fields update given the momentum. And that's somehow dictated by this Hamiltonian or energy function in a way that I won't go into immediately. But we should talk a little bit more about this inner product and then the update of the momenta. So the inner product is not too difficult to define. It turns out that for reasons based on the fact that this is in the Lie algebra, we can think of this as some kind of vector space, and the appropriate inner product on this space up to some normalization should just be defined as the trace of the matrix product of these things. So very straightforward to evaluate. This inner product is, and if you think about what the trace of such a matrix means, it actually ends up being the absolute value squared of every element of the matrix. So it's a very simple kind of norm type function on a matrix, and it happens to be the right one for the geometric space that we're talking about. Okay, so that's what this inner product means. And then the question is, so having defined what a small step of u looks like, what does a small step in time, in fictitious evolution time, of the momentum look like? So this can schematically be written as, well, sorry. This can schematically be written as the derivative of this variable with time should be equal to negative the derivative of the action with the link variable. But this is a matrix variable, so this is not really, I need to define what I mean by the derivative with respect to a matrix. And precisely what I mean is a bit technical, but I would like to just jot it down in case this is something that piques your interest. So we can define this in some way in terms of if I would multiply if I would multiply my link variable with some small update, differentiate with respect to the parameters of that update, where the TA are the basis vectors in this Lie algebra space. So there's some kind of basis matrices that could compose all the possible trace zero Hermitian matrices. You can probably start to imagine what those look like. for example, diagonal matrices that have trace 0 and off-diagonal matrices, excuse me, that have x and x dagger below and above the diagonal. Sorry, x and x star, for example, and elements below and above the diagonal. Anyway, the details of this are not really important to the story, but are necessary to understand if, for example, you want to implement this numerically, because you really need to know what that derivative means so I can get numbers out of my configuration to update my momenta. So this is kind of the high-level picture of how this works, and you may note that the updates of the momenta collectively depend on the entire action. So now if this action was local in the same way as we had looked at before, if we restricted it to just the gluons, so it really is truly local, then the forces here, in this fictitious Hamiltonian sense, the forces that update the momenta are really only going to update momenta on links that are near, according to, sorry, terms of the action, so as a function of links that are near the link that the momentum is associated with. So you get this localization of the force, and really a fairly similar kind of idea, just now done across the entire set of degrees of freedom at once, where we update some kind of momentum terms, and then we update the links according to the exponential of the momentum, very similar to how we did single link updates, but just now in principle across all the lattice at once. So taking small time steps now in the momentum and in the link space. But if the action, if we include, for example, the quarks, then there's this kind of non-locality because you just have this fall off, but you don't have a strict truncation in which links are allowed to talk to one another. So then you have the same structure here in that the momentum depends very strongly on the values of links near the link the momentum is associated with, and you have kind of a falling off dependence as you go farther and farther away geometrically, but never reaching 0. So you do in principle get a contribution from everywhere, and the nice feature of this is that sort of calculation is just as expensive as you would have needed to do if you had done a single link update, but now I'm updating all the links at once based on that calculation. So you somehow benefit quite a bit by being able to collect up all of these, the effects of the shape of the action on the links into this fictitious Hamiltonian dynamics picture. But that's not the only benefit. I think this is well outside the scope of my talk, but maybe this is something that Manuel will touch tomorrow, I'm not sure. That really another benefit of this hybrid Monte Carlo approach is that you can move very coherently for a while in a given direction in configuration space, because you have some momentum that's driving your motion. And so rather than imagining kind of a Markov chain process where you diffuse out from some initial configuration and you randomly go forward, randomly backward sometimes, this in principle can avoid that diffusive behavior and have a more efficient, so less autocorrelated updating scheme.
I have some practical questions. Can you integrate these dynamics analytically, or you need numerical?
You need to do a numerical integration.
Yeah. Because in statistics we do that, and then we do a measure resisting.
Yeah. Very good. So this is exactly next on my list. So thank you for the reminder. This is worth discussing very briefly. So as you say, we have to do some kind of numerical integration. And the usual approach is to do some kind of area preserving integrator, like a leapfrog integrator, for example. And all this means is that if I think of my pi and my u variables, I take a step starting with dt over 2 in the pi variable, and then conditioned on that, I take a step of dt and u, and so on. And ultimately, I take a final half step in pi. And the point of this is that you don't pick up a Jacobian even for a finite time step from this sort of an integrator. But there will be integrator error. And so, yeah, I should have mentioned this earlier, and thanks for the reminder. This is not precisely energy conserving. And so we do need to account for the fact that the measurement of the Hamiltonian may change over these dynamics, even though in principle, the underlying differential equation should preserve the Hamiltonian exactly. so preserve the energy exactly. But for finite time stuff, that's not the case. So you do need some kind of Metropolis Hastings at the end, which again has a probability based on, in this case, minus the Hamiltonian of the new variables divided by the Hamiltonian of the old variables. But of course, the advantage of such a scheme is that unlike for the single link updates we were talking about, here the Metropolis Hastings acceptance probability can be driven arbitrarily close to 1, even for very long trajectories, simply by reducing the discretization step of your integrator. So somehow the acceptance probability becomes independent of the distance moved in configuration space, since we're not taking the ratio of the two Boltzmann weights, but rather the ratio of the two Hamiltonians. And so even though you're exchanging this kind of, well, fictitious energy between the momentum and the link variables, you mostly should conserve the total energy, and so the total probability in this joint space. Yeah, so that is a good point, and this is something that is certainly a necessary step, because in practice in QCD, you tune the step size, but then you'll still have a fairly non-trivial rejection rate, maybe something like 30–40% rejection rate. Yes. Yeah, so it's a good point. I mean, there are schemes, I guess, where you can do this like partial refreshing of the momentum as you go, which would be in some sense introducing randomness into the dynamics. But at least the version used in modern lattice QCD calculations in particular is the one where you initially generate these momentum variables and then just deterministically evolve the pair, and then perform a Metropolis Hastings step at the very end. Sure. Yeah, I think there's a lot more that the lattice community could do in terms of playing with variations on a scheme, in terms of, well, both how do we do maybe the generation of the momenta and the integration, but maybe there's something worth considering in this Langevin-like approach where you can have a continuous forward integration and refreshing or introduction of randomness as you go forward. And I think there's some preliminary work from a while ago of people comparing these various methods, but the scope is very different in modern calculations. So it would be interesting to ask the same questions again at the latest state of the art, something like that. Okay, so I think while there would be maybe a little bit more to be said about Hamiltonian or hybrid Monte Carlo, I think in the last few minutes it would be nice to just talk about, in broad strokes, what are the major remaining obstacles. So while this method does work fairly well in terms of reducing your autocorrelation time, there are still major numerical challenges, which is why these calculations take supercomputer time. And so I'd like to just kind of conclude by going into that a little bit, and maybe that leaves some nice food for thought for whether some improvements could be made as we go to the future. So I guess briefly in words, I mean, the major considerations with all these schemes that are based on MCMC is what is the cost per step? And then what is the autocorrelation time in terms of the number of steps in your Markov chain? And of course, the longer the autocorrelation time, the more steps you need to take to get an equivalently decorrelated sample. And so therefore, the more steps needed for a similar statistical power. And so we've seen a little bit of the trade-off in terms of the cheapness of single link updates that work well when you have a totally local action, like in the purely gluon case, versus the typically more expensive hybrid Monte Carlo, which is unfortunately needed when you introduce the determinant that comes from the quarks. But even so, these are all MCMC schemes, and they all suffer from the same kind of critical slowing down type problems and autocorrelations that are worth a quick reminder and a quick discussion in the context of these particular QFTs. So one thing I'd like to mention that is a somewhat unique feature of these sorts of spaces is topological freezing. So we've seen in the context of the Ising model that maybe you have something like two potential wells, and it becomes very difficult to move between the two of them as your number of degrees of freedom grows. But there's a symmetry that relates the two. And so as physicists, we're maybe happy to just sample only from one of the two potential wells and just by symmetry understand that the physics will be the same in either case. That's not necessarily the case when there's the potential for some kind of topological winding number that may appear for some configurations and not for others. So just as kind of a cartoon picture, if we draw a similar sort of structure here, we could draw, for example, the potential with respect to, well, some abstract notion of the configuration space. So let me write this as the action rather than potential to use the specific notation here. And you might expect to see something like the following, where you have multiple different minima with slightly different actions that corresponds to different winding numbers. So I can denote this winding number by Q. And the idea is this is really some kind of high dimensional winding, very akin to what you'd imagine for, say, a string winding around a cylinder or a string winding around a circle. So you could have a string that doesn't wrap around a circle at all. This is some Q equals 0. You could have a string that wraps once around a circle, etc., right? And if you were to try and transform from one to the other via some kind of Markov chain Monte Carlo, you would expect some potential barriers between these configurations that really slows the mixing as you try to move from one such local minimum to the other. And that's exactly the case already with just gluons in QCD, because there are arguments that one can make that as you take the lattice spacing small, there are these continuous field configurations that you can write down that correspond to 0, 1, 2, -1, etc. winding numbers, with the only differences between these minima being some small but non-zero differences in the potential. So unfortunately, there's not a symmetry relating these different sectors. It would not be enough to just sample within one and kind of translate the observables that you see to every other minimum. And really, for example, the volume within each of these different minima might be quite different. And you need to appropriately sample respecting the relative volumes between these minima. So we're really forced in that sense to confront this problem and find, hopefully, maybe something like a coherent cluster-like update that would let you move from different topological sectors, although none are known presently. So this is one of the major problems. There is not a good solution, so this is something that work continues forward on. Independently, maybe, or along a similar but slightly different vein, there is more ordinary critical slowing down as well. So as you take the lattice small with this kind of infilling, as we were just discussing, because I'm imagining that I'm really refining the physical space and let's say the length scales remain the same as I have more and more refinement at smaller lattice spacings, that means that correlations that used to take, for example, 3 lattice sites, then take 6, and then take 12, and so on. And to propagate such correlations or to stochastically sample with fluctuations that have such long ranges starts to look a lot like the challenges of sampling the Ising model near criticality, where you have patches that should fluctuate similarly, but those patches involve many, many lattice sites. In fact, a growing number of lattice sites as we take the lattice spacing towards 0. So this problem is a bit independent of the topological freezing problem, but they both result in growing autocorrelation times, especially as the lattice spacing goes to 0. So again, this is something that at least a let's say, an impactful solution is not known for. There's mitigating approaches, for example, like using hybrid Monte Carlo with good tuning. But nevertheless, you expect the divergence of the cost as to draw independent samples as we take the lattice spacing towards 0.
So HMC doesn't completely circumvent.
HMC does not completely circumvent this, yeah. And in fact, that's one of the slides that I thought I might just flash. Yeah, I'll just share this for 2 seconds. Okay, hopefully you can see this plot. On the y-axis is the integrated autocorrelation time. So this is the measure of how many steps it takes to decorrelate in the Markov chain. And on the bottom is the lattice spacing measured in femtometers. So as you go to the left on both of these two plots, that's going towards the continuum limit. And I apologize, the text is kind of small, so maybe it's hard to read from the back, but the orange curves are running HMC, and this is fitted against power laws in the lattice spacing in terms of the divergence of the autocorrelation time. And even for a non-topological observable, we see a divergence with a coefficient of maybe 1.2 in terms of the lattice spacing. So there is a power law divergence as you go towards 0 lattice spacing, despite using HMC. And it's actually not too dissimilar from using other methods like heat bath, which is given in HB and the other colors there. So this is indeed a real problem. Okay, so these are kind of the main challenges. And as I mentioned, really, there's also a practical challenge, which is the inclusion of the quarks. Because we have this rather irritating determinant, which is in terms of some matrix that's a function of the gauge links, the gluon field, rather. And this is non-local and requires, in principle, some kind of matrix operations on very large matrices. So there's also practical challenges which drive the computational cost of this sort of a problem. Okay, so these are the kind of main considerations, and I would say the struggle against that is ongoing. We make practical improvements, but there's no real kind of killer new Markov chain Monte Carlo scheme or other sampling scheme that seems to solve these. So sampling remains a bottleneck in QCD. So what I would just like to highlight is maybe some promising directions in the last 2 minutes or something. So while standard HMC with some practical improvements works quite well, there would, in principle, probably be some gains to be made from just better tuning HMC parameters. So for example, you have the integrator that you choose, the step size, maybe the initial distribution of momenta. This kinetic energy, for example, that I added is completely artificial, so I can rescale the momenta, and this actually changes how rapidly, for example, different links move with respect to one another. So we could, in principle, try to find better motion in the space by tuning those sorts of parameters. A sort of interesting one, since we were talking about boundary conditions before, would be to modify the boundary conditions. And it actually turns out that this topological problem has to do with the fact that we're using periodic boundary conditions. If you just open all the boundaries, then sort of topological defects can flow into and out of the volume freely. And so while you do still have these different minima, they can be now maybe much more easily deformed into one another because you have this approach to move topological charge around. It would be sort of like cutting the string in this winding number analogy. So you can now easily wrap or unwrap the string around the circle. So this is sort of interesting, but you lose then the nice properties that you now have a lot of boundary physics to contend with. Is important for certain analysis. Just a couple more options to mention. There's also what I think is kind of an interesting approach to use parallel tempering. And the idea here is just to run several different Markov chains simultaneously, where maybe you have some of them tuned to coarse parameters and some tuned to fine lattice parameters, and you allow, in principle, exchanges between these, with the idea being that since the coarse Markov chain will mix much more rapidly, hopefully you can regenerate, let's say, the long modes very quickly, and then have a lot of proposed swaps successfully accepted to update the lattice at the target parameters. The problem here being, what is the swap rate versus the number of chains? So you now have to duplicate a lot of work because each one of these chains is a chain of very large configurations. So extra memory, extra cost, etc. And yes. So what I mean in that sense is maybe more akin to, well, this, I don't know what you said, Sam, outfilling, where you have the same number of degrees of freedom, but you just are retuning how close together they are. So you don't change the number of links or sites, you just retune how close or far apart they are. Yeah. Okay, and so then finally, just to kind of leave off, because this is the sort of stuff that I personally work on, I think it's also interesting to look at these kind of optimal transport or some kind of normalizing flow types of approaches, where you can move in principle from some easy distribution defined by, let's say, an easy action through a diffeomorphism acting on the configurations to hopefully something approximating your target distribution by building in correlations in principle through this kind of transformation. So there's a lot of, I would say, new ideas on the market. None of them have borne fruit at the scale of Lattice QCD, but this is something that we continue to look at. Yeah. Mm-hmm. They become exact when you introduce a Metropolis Hastings step. What is not going to be free? Sorry.
Very small lattice space.
Mm-hmm.
And the signals are really not with very small data.
Yeah, I think that is the case. So I think especially what's challenging, at least my understanding of these methods in the QCD context, what's especially challenging is as you increase the number of degrees of freedom. So it might be okay if the lattice spacing is relatively small, but you're only working on a small region of space. So if you have few degrees of freedom, but the lattice spacing is small, this is something that in principle seems to be possible to sample. But if you go to, let's say, fix the volume and then do this infilling where you increase the number of degrees of freedom, this can be quite costly. I agree.
Is it expensive to compute the global, the Hamiltonian to each step of your, after you've completed each iteration of your leap from?
For the Metropolis Hastings step.
Yeah.
It's about as expensive as computing the forces to update the momenta at each step. So you just have one of those calculations at the end. Yeah. So in that sense, it's not too bad. Yeah.
You were saying that the number of degree of freedom can go be high, but even for so why? Like you said at the beginning it was like 19 degrees of freedom.
So these are different degrees of freedom. So on the one hand, you have 19 free parameters, which I should call hyperparameters. So those are things like this constant beta that goes in front of your action. But the degrees of freedom that I'm talking about are really the variables inside your action, the field degrees of freedom that you're integrating over. And those are values that are placed on every, let's say, link of the lattice. You have some matrix that's placed on every link of the lattice. And as you refine your lattice, you have more and more links, and therefore you have more and more matrices to hold.
And the underlying physics that are behind the problem, is there a lot of dimension in degree of freedom or not? Because what I meant to say is, like, for example, the algorithm of optimal transport and score diffusion, for example, work well on faces, but it is a conclusion of the fact that spaces have a really small degree of freedom, actually. Like, and is it the case in the physics as well, or not?
I mean, fundamentally, this would be, I think, really pushing the boundaries of what optimal transport could do. I mean, the idea would be to act on these maybe trillion degrees of freedom at once, at least in the naive approach, where you try to map your entire field configuration from maybe drawn from a simple distribution through some map to be distributed according to your target distribution. And it is a big challenge, I completely agree. But given the obstacles we face, I think it's worthwhile to continue exploring as many avenues as we possibly can afford at this point. So there's a lot of options on the table, and hopefully one of these will crack the problem and push the frontier enough that we can hopefully answer some interesting physics questions in the next 5-10 years. That's really my hope. So, well, with that, thank you for your attention. I appreciate the striving to the end of the evening.
What do we do? We can finish the recording?
Oh, yes.
We have someone showing up this evening who will have plenty to talk to you about the parallel.
Great.